There we go. Today we're going to cover section 2.2, or at least get started on this section. We're going to look at more proof methods. Last time we looked at section 2.1, where we learned how to do direct proofs. And we were mostly proving implications of the form if P then Q. And we also looked how to prove that theorems are false, that they're not actually theorems, using counterexamples. And that's where we came up with an example to show that a universally quantified statement is false. So if you're claiming that everything of a certain category is true, we can come up with an example where that's false for our counterexample. And we're going to look at, I think, 5 more different methods of proof. They're called different methods, but they're kind of all versions of the same logic, and I'll tell you how the logic of these kinds of proofs is connected to the more direct logic that we talked about last time. So our first example here is proof by contradiction. So the idea, just to give it a good definition, is that usually, and I should have used a different word here, we can establish the implication if P then Q by assuming that P is true while Q is false. And you should remember from the truth table for the implication that if P is true and Q is false, that the implication itself is a false statement. So if we're trying to prove that this is actually true, and we're assuming that P is true and Q is false, then what we're actually looking for is some sort of contradiction, some issue, because we don't want this to happen, or we want to show that it can't happen, rather. So we're looking for some contradiction, and usually a contradiction looks like this, where a statement is both true and untrue, true and false. And this is impossible, of course. Something can't be both true and false. So the idea here is that if we can find this contradiction from our assumption that P is true and Q is false, that means that the implication itself can never be false. And that establishes that it's true. So it's a backwards way of thinking. And this is sometimes called an indirect proof. Because we're thinking in kind of this backwards way. And the way this relates back to the logic that we learned in chapter 1 is this. We showed that the implication, if P then Q, is logically equivalent to this proposition, which says it's not the case that P and not Q. So what we're doing is assuming the inside that P is true and Q is false, and we're trying to show that it's impossible. So it's not the case that P and not Q. And this is what a proof by contradiction looks like logically. So let's go to an example to see how these work. But actually, after I wrote my notes, I decided to use a different example, but I didn't have time to replace this page on Blackboard. So we're actually going to look at this, this other example that says for every integer n, if n squared is even, then n is even. And we're going to prove this by contradiction. Okay, so you're asking how do you know where to start? If we're going to prove an implication, an if-then statement by contradiction, we're going to assume that the hypothesis is true and the conclusion is false. So if we get started writing, we might say something like, by way of contradiction, to let the reader know what we're going to do, and then we're going to assume that the hypothesis is true, that n squared is even, and the conclusion is false. In this case, the conclusion is n is even, and the negation of this would be that n is odd. So even turns into odd. So we're going to use these two facts to try to come up with a contradiction. So to come up with a statement that's both true and not true at the same time, which is impossible. So what we want to do in this case is look at n and then try to square it to compare to n squared. Because squaring a number, multiplying it by itself, is easier to understand than trying to take a square root. It's not really clear what we would do if we were trying to take a square root. So we're going to look at n, we're going to focus in on n, and then square it. So since n is odd, we know that it's equal to 2k plus 1 for some integer k. Let's write that down next. Remember, this is what it means for a number to be odd, for an integer to be odd. Okay, so if n is equal to 2k plus 1, then we can square it. N squared is equal to 2k plus 1 squared, just substituting n. We'll have to FOIL out here. Maybe we'll write all of it. We get 2k times 2k. Let's write out all the details. So we get 4k squared, and then you'll get a 2k times 1, another 1 times 2k, and then a 1 times 1. So let's work this out and simplify it to see if we have an odd number or an even number. And you can probably already tell, but I want to make sure we have all of the details included here. So first thing, you should combine the two k's. You'll get a 4k squared plus 4k. And we know that if we have an even number, we should have 2 times an integer here. And if we have an odd number, we should have 2 times an integer plus 1. And this plus 1 on the end tells us that, in fact, we are looking at an odd number, because we can factor out a 2 from the first part, 2k squared plus 2k plus 1. This means n squared is an odd number. Okay, so let's look at what we have. Our assumption at the beginning was that n squared is even and n is odd. But after we worked through what it meant for n to be odd, we came to the conclusion that n squared itself is odd. So we have two statements, n squared is odd and n squared is even, that are impossible to both be true. So if you're odd, you can't be even, and if you're even, you definitely can't be an odd number. So we'll conclude by saying this contradicts our assumption that n squared is even. Oops, and you can't see my last line. And that finishes the proof, because we found the contradiction. Okay, are there any questions on what we did or how that works? So I'm not going to have time to also work through this other example, the original one that I had, but what I want you guys to do is, well, read your textbook. And that's an example in your textbook. It's example number 2.2.3. On page 73. So this is an important example showing that the square root of 2 is irrational using a proof by contradiction. So make sure you read over that one and understand that one too, before you try your own proofs by contradiction on the homework. Okay, so no questions? Then let's move on to the next example, which is a proof by contrapositive. Looks like my grammar got a little mangled here. Guess I was distracted when I was writing this. We saw in chapter 1, to fix the grammar, that the implication, if P, then Q, is logically equivalent to if not Q, then not P. And this is what we called the contrapositive. And I know I told you back in chapter 1 that the contrapositive was going to play an important role going forward. And this is the most important role of the contrapositive. Because anytime we see an implication or a conditional statement like this, it's actually the same as its contrapositive. And sometimes it's easier to look at the contrapositive than it is to look at the original conditional proposition. Like in this example, that says, prove that for all x in the real numbers, if x squared is irrational, then x is irrational, using a proof by contrapositive. And this example has the same kind of difficulty that the last one did. If we went at it directly, if we just assumed the hypothesis and tried to show the conclusion directly, then we have the issue of getting rid of the square. In order to get rid of the n squared, we would have to take a square root. And on this problem, in order to get rid of the x squared, we would have to also take a square root. So in order to avoid that difficulty, we want to think in a backwards way, using the contrapositive. We want to assume that the conclusion is false and try to show that the hypothesis is also false. So let's set up our proof. Remember, you always want to start by letting the reader know what you're doing. So in this case, we're going to, instead of proving this statement, prove the contrapositive of the statement. And we should also write out what that actually means. So if this is false, x is irrational, that means x is actually rational. So if x is rational, then we need the negation of the hypothesis too. This says x squared is irrational. So the negation is x squared is rational. So now we're going to assume this, x is rational, and try to show that x squared is rational. Does anyone remember what a rational number is? What does that mean? Fractions, right. We're assuming that x is a fraction. So that means there are integers, a and b, where x is equal to the fraction a over b. And our conclusion involves the number x squared. And in order to get x squared, we'll just square what we have here. So we could say, therefore, x squared is equal to this fraction squared. And we know how to square fractions. You just multiply, or you just square the top and the bottom. A squared over b squared. So what can we tell about a squared over b squared compared to the conclusion that we want? What can we say next? Right. So now we have x squared written as a fraction. So we know it is also a rational number. And that finishes the proof. Good. Okay, any questions over this proof by contrapositive? Okay, so if there aren't any questions, we'll just keep moving along and work through some more examples. This is another common proof method, and often you'll combine this method with another one. The method of proof by cases is used when the domain, or the domain of discourse, the things that you're talking about, can be naturally divided into multiple cases. And I mean things like positive and negative, or maybe odd and even. So those are some simple kinds of divisions. So positive and negative, this could apply to real numbers. And odd and even, that could apply to integers. And there's lots of other kinds of things, lots of other kinds of statements where the domain of discourse can be divided into pieces. I'm sure we'll see more as we go along, but these are the simple ones that you'll encounter at first. And we're going to look at this example. Prove that for every real number x, x is less than or equal to the absolute value of x using a proof by cases. So this kind of statement, x is less than or equal to its own absolute value, might seem a little bit obvious, but even obvious, or statements that feel obvious, they still need to be proven to be actually true, so that we can be, totally 100% certain that we're on concrete ground. So here we're looking at real numbers, and this is going to divide itself into cases. Oops. Should start with the word proof. Getting a little bit ahead of myself. So we're going to use a proof by cases. So we'll let the reader know that. And the cases for real numbers that often work are where your number is greater than or equal to 0, so it's non-negative, or it's negative, so x is less than 0. So the reason why I can't say just x is positive or x is negative is that I have to worry about what happens when x is 0 itself, and, well, 0 is neither positive nor negative. So there's a few ways you can write your cases. In your textbook, the cases are just included in the discussion, but you could also use something like subtitles. So we start with a proof, we will use proof by cases, and then you could say something like case 1. We will assume x is greater than or equal to 0. So in this case, where x is greater than or equal to 0, let me write a few of those words. In this case, the absolute value of x, since x is greater than or equal to 0, is actually equal to x itself. And that actually finishes the whole case. We've shown that x is less than or equal to its own absolute value. In this case, it's equal to. Does that make sense? And please stop me if I'm going too fast or if I say something that doesn't make sense to you. For case 2, we're going to assume that x is negative. So you could say something like, now we will assume that x is less than 0. In this case, the absolute value of x, since x is negative, is actually going to be equal to negative x. So we're putting a negative sign on a negative number to get something positive. So just to illustrate this, if you were taking the absolute value of -4, then we know the absolute value is 4. But this is also negative 4. The two minus signs cancel each other. So if x, the absolute value of x is equal to negative x, we know that this is going to be greater than 0. It's going to be a positive number. How do you know which sign to use with less than or greater than? Are you asking about these two or this one? This one here. Okay. The assumption here. So here we've broken down the real numbers into two cases. So if we were looking on the number line, what we've done is we've broken it at 0, and let's see, do I have a different color here? Yeah. So we've said that if you start at 0 and go this way to the right, this is my first case. That's where x is greater than or equal to 0. And if I only look to the left, this is the second case. So I've just divided up all of the numbers into two pieces. And the order of your assumptions, it doesn't really matter. We could have started with the negative numbers and then done the rest of them, the ones that are greater than or equal to 0. As long as you have both cases, it's fine. And looking at this other inequality, we started with this one. X is less than 0 in case 2. X is negative. If you multiply both sides by -1, if I put a minus sign on the left side, basically, we know it's going to flip the direction of the inequality. So if I put a minus sign here, we get a greater than. That's what I'm doing here. And I can extend this inequality a little bit because I know x itself is less than 0. So I can put x over here. So minus x is greater than 0, and 0 is greater than x. So when we string all of this together, we can see that what we started with, the absolute value of x, is greater than what we ended with, x. And that's what we were looking for. So if we start with a number greater than or equal to 0, we end up with something equal to its absolute value. If we start out with something less than 0, then we have something that's less than its absolute value. So that completes the proof, since we've done both cases. Are there any other questions about this third example? Okay, so William is asking if the number of cases can change depending on the question. And the answer is definitely yes. For these simple kinds of proofs that we're going to be doing for now, most often you'll have two cases like this, or maybe you need to divide the integers up into even and odd cases. Let's see if I can find an example. Yes. So your textbook has an example where there are actually 12 cases. Oh, excuse me, this is 3 times, yeah, 12 cases, that's right. And each case corresponds to plugging in a number. But you'd have to read through that whole example in your textbook to really know what I'm meaning. But going back to the number line, we could also divide the number line up into different ways. So maybe, for example, this could happen. You might need to divide your number line up like this. So here's -1, here's +1. So maybe you need to take all the numbers from -1 up to +1 and treat that as a case. Well, if we want 3 cases, let's make 0 its own case. and then maybe all of these numbers, and then all of these numbers. So your cases would be maybe something like this. So case 1, that should be a colon, would be something like x equals 0. And then your case 2 could be where, what's the easiest way to write this? Where the absolute value of x is greater than 0 but less than 1. And then your third case could be where the absolute value of x is greater than or equal to 1. So where you're on the tails. And the interesting thing about proofs is that there's often many ways of proving a statement, and different students or different people can choose different ways to prove things. And this is one way that proofs can be different. You might choose to divide up your cases differently. So sometimes it's just up to you to pick them. Let's see. Any other questions? Okay, so it looks like we have time for at least one more. So this is the fourth kind of proof that we're looking at in this section, proofs of equivalence. And you might remember what an equivalence is, or a biconditional statement. That was another word. Remember, biconditionals look like this. It's an arrow between your two simple propositions pointing both directions. And remember, this meant that it is true, this biconditional statement is true if P and Q both have the same truth value. And one thing that we did back in chapter 1 is show that the biconditional is logically equivalent to two conditional statements. P, or if P then Q, and if Q then P, like this. So the usual way to prove an equivalence, which is a theorem of this form, is to prove two conditional statements. And here's the example that we're going to be working through. We want to prove that for every integer n is odd if and only if n minus 1 is even. In this collection of words here, if and only if is the biconditional logical connective. So instead of trying to prove this all at once, we're going to prove two conditional statements. We're going to say if n is odd, then n minus 1 is even. And then we're going to flip it around and try to prove if n minus 1 is even, then n is odd. maybe one more thing I'll mention, that you might think of this as a kind of proof by cases. It's not maybe a precise way of thinking about it, but in this proof, we're doing two things. So we do have two cases that we're looking at. But our cases are a little bit different because they're actually different logical structures. So you want to let your reader know what you're doing, that you're going to start by proving this implication. So maybe just say that. We will start by showing that if n is odd, then n minus 1 is even. So in this, if n is odd, then n minus 1 is even. We're going to assume the hypothesis that n is odd. And remember what that means. There is an integer k where n is equal to 2k plus 1. And now we can see what we get when we subtract 1 from the number. So n minus 1 is equal to this stuff, 2k plus 1, minus 1. And then just simplify. This plus 1 will cancel with that minus 1 to give us a 2k. So n minus 1 is equal to 2k. That means n minus 1 is even. And that's what we wanted to do in this part of our proof. We showed that if we assume n is odd, then n minus 1 is even. Okay. So we've proven, going back up to what we were doing originally, we've proven this part of the biconditional statement. Now we need to show the other part is also true. So we need to reverse the order and look at the converse. So let your reader know what you're doing. So we're going to show that if the right side, n minus 1, is even, then the left side, n is odd. So now we're assuming n minus 1 is even. And then interpret for your reader what that means. That means there's another integer. We've already used the letter k. we can just go to maybe the next letter in the alphabet, maybe letter L. And when you're writing L's by hand, when you're writing a proof out by hand, it's a good idea to use the cursive L instead of the print L, because it's impossible to tell the difference between a 1 and an L if you're just writing it most of the time. So try to use the cursive version. So if n minus 1 is equal to 2k, then we can add 1 to this to get n. So n is equal to n minus 1 plus 1. But we can substitute in 2k for the n minus 1 part. So now we have an equation that says n is equal to, oh, and I switched letters here. N minus 1 is 2L. Need to be consistent. N is equal to 2L plus 1. Yes, yeah, you could start by using algebra. You could start with this equation and just add 1 to both sides. That's totally fine. Yeah. Either way, you'd still end up with the same equation. N is equal to 2L plus 1. And this equation tells us that n is odd. So either way, you still get to the same conclusion. And that completes the proof. We've started with n minus 1 being even, and we've shown that n is odd. And we also finished the biconditional part of our proof, or the second part of the biconditional, this one here. Okay, so it looks like we're out of time for today.